Alright, on this card we're going to talk about the word concurrent. Okay, this is one of those words we have to know in geometry. So, lines that contain the same point are called concurrent. Okay. Concurrence, let me think here. Concurrence is the concept of three or more lines intersecting in a single common, we'll put that in parentheses, point. Okay? Comma, or in other words, having a single point of intersection. And we're going to see exactly what that means. Okay? So, that's concurrent. Let's put that aside. The next thing we want to talk about is what's called a median. Alright? A median of a triangle is a segment joining any vertex to the midpoint of the opposite side. So let's see an example of what this looks like. Okay, so first we're going to draw a triangle. So I'm going to go from the 1.5 to the 4. Then I'm going to go up 2 inches, 1, 2, 3, 4, 5, 6 to the 6th line. So you can line it up how I am here if you want to follow what I'm doing. It doesn't have to be exactly like this, but then I'm just going to connect those sides. So here's our triangle. Okay. Now, this side I made 2.5 inches long. So half of that would be 1.25 right here. So a median goes from the vertex. That looks way too much like an altitude. So we're going to do this card over again. All right. So let's talk about median. A median of a triangle is a segment joining any vertex to the midpoint of the opposite side. Okay, so let's draw a triangle. I'm going to go from the 1 to the 5. Then I'm going to go up 2 inches. So I'm going to go up 1, 2, 3, 4, 5, 6, 7 lines. And then I'm going to just connect these 2 sides, and then we'll have our triangle. And I'm going to draw a picture of what a median is. Okay. So we choose any vertex that we want. There's 3 vertex, right? That's the corners of the triangle are the vertex or the vertices. So I'll choose this top one. Now, the median goes from the vertex to the middle of this opposite side. So I'm just going to quickly look and see where the middle is. If this side is 4 inches, then the middle is right at 2 inches. So that's where the median goes. It goes from the vertex right down to the middle of the opposite side. So what we know is that this piece is the same length as this piece. Okay? So let's just label this triangle A, B, C, and let's make this point D here. So BD, segment BD is a median. So that tells us that AD is congruent to DC, because a median cuts the opposite side in half. Okay, that's the definition of a median. See, it joins any vertex to the midpoint of the opposite side. All right, the midpoint is the point directly in the middle, which cuts this whole piece in half. So these 2 pieces are then equal. All right, that's much better. Now let's next definition is for centroid. Centroid, okay? Let's see. The medians of a triangle are concurrent. So that means the medians of all the sides of the triangles will meet at a special point. Okay? and that point is the centroid, but hold on, we're going to write that. So the medians of a triangle are concurrent. Let's see. The point of concurrence is in the interior of the triangle and is called the centroid. Okay? Now, let's see what else we could write about this. Okay? Let's see. Let's skip a line and put down the centroid is the center of gravity of the triangle. Okay? And then one of the most important things, let's skip a line. The centroid divides the medians into a 2-to-1 ratio. Okay. The section of the median nearest the vertex is twice as long as the section near the midpoint of the triangle's side. Okay, let's see a picture of this. So let's turn the card over. I'm going to line my ruler up right on the bottom and on the 0. And again, I'm going to draw from 1 to 4. This time a little. Let's just go to 5. From 1 to 5. Then I'm going to go up on a slant 2 inches. Doesn't matter how much of a slant. The triangle doesn't have to be perfect. Alright, it's just a drawing of a triangle. That's it. We could have drawn this any way we wanted. So, now, what I'm going to do is find the middle of this side and just put a little mark there. This side is 4 inches, so 2 inches is the middle of that side. So let's draw our first median. Alright, the first median goes right from the vertex to the midpoint of the opposite side. Now, let's measure this side was 2 inches, so right at the 1 is where this median is going to touch, from this vertex to the middle of this side. So this is our second median. Okay. And we have one more. This side is, I'm going to line it, I'm going to find the middle of this side. This side is about 3 5/16. Okay, so that's about a little more than 1.5. So let's see here. It's about 1.5 and a 16th, so it's a little more than 1.5. I'm going to make a just a little mark. Now, I don't really have to make a mark there because I know it's going to go through that middle point. So, see, my mark was close, but not perfect. So I'm going to just line up the ruler on this vertex and on this center point, the centroid. Okay. So there we have all 3 medians drawn, right? And there, now we know that this side is congruent to this side because this median cuts this side in half. And we know that this side is congruent to this side because this median cuts that side in half. And we know that this side is congruent to this side because this median cuts this side in half. Okay? Now this point of concurrence where they all meet, that's the center of gravity for the triangle. That's called the centroid. Okay? So now that's a special point because it divides the medians in half. It divides them in a special way. The longer piece near the vertex is always twice as long as the smaller piece. So let's draw in some numbers here. So if this was, let's see how I can do this best. So if this was 10, this would be 5. Okay. If this was 8, this would be 4. Okay, and let's say this one was 12. Then this one would be 6. Okay? See how that works? Now, that's about all we need to write, because that makes it pretty self-explanatory. Okay? The little piece is half of the big piece, only when you have a centroid. Okay, you see how all the big pieces are twice as long as the little pieces? Okay, so that's a good enough picture for centroid. That's a really important concept. Let's put that card aside. Let's look at the next card, which is about altitude. Okay. An altitude of a triangle is a segment from any vertex perpendicular to the line. So from any vertex, and then it's perpendicular to the line containing the opposite side. Let's just go back to centroid for a minute, and I'm going to put in this bottom corner a little curvy arrow to remind us to flip this one over. Okay? So altitude. An altitude of a triangle is a segment from any vertex perpendicular to the line containing the opposite side. So, let's draw a picture of an altitude, and I'm going to draw two different triangles here. Okay. Let me think how I want to draw these. I'm going to draw my first triangle from 1/2 inch to 2.5 inches, the base. And my second triangle I'm going to draw from, let's think, 3 1/4 to 5. Okay. Now I'll show you how I want to draw this first triangle. We're going to make this an acute triangle. Okay, so hopefully you remember the difference between acute and obtuse. Now it doesn't have to look exactly like mine, okay? This is going to be my first triangle. This is my acute triangle. All the angles are less than 90 degrees. And on this other triangle I'm going to draw an obtuse triangle because there's a difference in the altitudes. And you'll see exactly what I'm talking about when we finish this. So in an obtuse triangle, one of the angles is greater than 90, right? The other two are less than 90. Okay? So, an altitude is a segment from any vertex perpendicular to the line containing the opposite side. Okay? So, if I was going to draw an altitude for this first triangle from this vertex up top here, now I want to draw this line as best I can straight down. It would go straight down like this, and it would be perpendicular. Okay, and now I can do that from any one of these vertex. I can go to this side straight down, or I can go to this side straight down, but I chose to go to that side. Now watch what happens when you have an obtuse triangle. Say I'm going to go from this vertex, I just go straight down. So in this one it's inside the triangle, and when you have an obtuse triangle, sometimes it may be outside the triangle. Okay, so in this case the altitude is going to look like this. Right? And usually what they do is they draw a dotted line like that, and they show this as 90 degrees. Okay? So let's label this triangle A, B, C, D, and let's label this one A, B, C, D. So segment BD is an altitude in this triangle, and segment BD is an altitude in that triangle. So sometimes the altitudes are inside the triangle, but sometimes they're outside the triangle. Okay? But anyway, you could just imagine being at the vertex and dropping a weight straight down. Alright? The altitude always goes straight down, as if you were dropping a weight. Okay? It always goes from the vertex straight down. Now we can also turn this triangle and drop straight down from here. Right? Or from this vertex we could drop straight down. Straight down to the ground. Alright? So that's altitude. Next, what we have is orthocenter. Okay? The lines containing the altitudes of a triangle are concurrent. They're concurrent. That means they all meet at one point. Okay? The point of concurrency, comma, called the orthocenter, is let's put may or may not be inside the triangle. Now, I think we have enough space to do it here. So, let's draw our first triangle. Okay. I'm going to make this one 2 inches long on the base. And then I'm just going to go up a little bit. And then I'm going to come back here. Okay, now the first thing I'm going to do is, I have my triangle, now I'm going to draw all 3 altitudes, and they're going to meet at a point in the triangle. Okay, when you have an acute triangle, the altitudes will meet at a point inside the triangle. So, first I'm going to go from the vertex straight down to this side. Okay. So that's one of my altitudes. But if I had my triangle this way, right, I would have another altitude. I would have an altitude there. Now I can also drop an altitude from this side. Alright, and the 3 altitudes, as you can see, will all meet at a special point, in this case, inside the triangle. And that special point that they all meet is called the orthocenter. Okay? Now, let's draw a picture of a case where the orthocenter will be outside of the triangle. And this has to do with an obtuse triangle. Okay? So let's think, how am I going to draw this? I'm going to need some space below it. So I'm going to make this 1.5 inches. Alright, and then I'm going to go up at an angle. Maybe I'll go right to that line, about 1 inch up. At an angle. And watch how this changes everything now. So this time I have an obtuse triangle, right? Now, let's say I want to draw from this vertex straight down. So what I do is I draw a line. Straight down from that vertex. And there's my right angle, and now I'm going to make that dotted line. Okay, so there's my first altitude. Alright, now I'm also going to extend my altitude down with a dotted line, just like this. Pretty much to the edge of my paper, and you'll see why I'm doing that in a second. Now, let's draw the altitude to this side. So first I'm going to draw, so from this vertex straight down, I'm going to draw my dotted line so I can see exactly where it is this thing is going to go. It'll give me a good reference point to draw that line down to. Okay, so now I'm coming from this vertex straight down. Right? And then I'm going to continue that line as well. And it looks like I might just make it here. So here's my altitude on this one. From this vertex down, if I was looking at the triangle this way, right? Now there's one more. This one is actually going to be straight down inside the triangle. So now I'm looking at the triangle just how it is, like this. So the altitude's going from this vertex down to this line. And what I'm going to do is extend that altitude also. And you can see that my orthocenter is actually going to be, in this case, outside the triangle. Alright? So there's two possibilities for this. Alright, let's go to the next vocabulary. And we have angle bisector. Okay? Let me just pull up the definition for that because it's not on the thing I'm looking at. 1 second. Okay. An angle bisector. So an angle bisector divides an angle into two congruent angles. Okay, then let's see a example of this. Let's say I had an angle like this. Okay, and I want to, my angle bisector needs to cut that in half. So this angle turns out to be pretty much 50 degrees. Okay, so I'm going to cut it into 25 degrees, would be directly in half. So that's where my angle bisector goes. And it could be a segment or a ray. In this case I'm going to draw it as a ray. So let's see, this was A, B, C, and D. So then ray BD is an angle bisector. And that means that the measure of angle ABD is congruent to the measure of angle DBC. That's from the definition of an angle bisector. So that means that this angle is congruent to this angle. So they each get one angle mark. Okay? So now what we have is, oops, give me 1 second. Okay. We have something called the in-center. The angle bisectors of a triangle are concurrent the point of concurrency comma called the in-center comma is let's see, may or may not be, no, is always inside the triangle. So, now there's another statement that we can make about this. The point of concurrence, instead, the incenter, let's cross that word out, the incenter is the center of an inscribed circle within the triangle. Okay? So let's make a little thing here to tell us to go to the other side. We're going to do our drawing on the other side here. Alright, now, this one I want to make a pretty big triangle for. I just want to make sure you saw the bottom of that. Okay? I'm going to go from the 1 to the 5. Nice big triangle. I'm going to go up high. This time I'm going to make it a little different. I'm going to go up high this way. And then I'm going to connect these two. Now I'm not really measuring this, okay, I'm just making a triangle. Okay, now watch this. First, we have to find the angle bisectors for all of the angles. So let's start over here. Okay, if I line that circle on that vertex, this angle is about 41 degrees. If I fudge it just a little bit, now it's almost 42 degrees. So that means my angle bisector is going, whoop, I just moved it. My angle bisector is going to be at 21 degrees. So I'm going to make a little dot at 21. Okay. And now I'm going to draw, and you could barely see it, but I see it clearly. It's right there. So now I'm going to draw my angle bisector. And it's going to go right from this vertex down the middle of this angle. So we just bisected this angle. Okay? So now let's do the same thing. Let's measure this angle. So I line my protractor up. Okay. Now this one is 80 degrees, right on the money. So I'm going to go to 40. Okay. I'm going to draw a line from this vertex right through that dot. Okay. I got one more angle to cut in half, and that's this angle. This angle's 60, so I made it easy for myself on accident. There's the 30 degrees, and see how they're going to all meet at one point? That's what we want. That's exactly what we want. So, let's see here. This point is called the incenter. Now let's just make a couple of marks on here to remind ourselves that these are angle bisectors. So we bisected this angle, so that means that this angle is the same size as this angle. So let's put one angle mark on each one. Now let's go to this angle. That one was bisected, but we can't put one because we already used one, so we put two angle marks, and we put two angle marks here because those are the same. And then on this one we're going to do three. 1, 2, 3, and then we do the same thing here. 1, 2, 3. Okay? So now we know that those are angle bisectors. So, our last part is to take out our compass. Okay. And so that is the center of the circle. So what we do, how do we do this? We put the center of the compass right on that center point. Okay. And we put the compass so that it's right on the closest point on the triangle to that dot, which I believe is that. Let's see. Yeah, that's going to be pretty good. So, what I did was I put it so that it's touching the side of the triangle, and now I'm going to use a pencil this time, and watch what happens. Boom. It's the center of what's called an inscribed circle. That means the circle is inside the triangle, touching it on its edges. Okay? So that's our picture. Now, let's see if there's anything else we needed to draw. Nope, that's it. Let's see what else. What's next? Now we have perpendicular bisectors. Let me just go to the formal definition for that. Okay. So our word is perpendicular bisector. The perpendicular, a perpendicular bisector is a line that bisects the segment and is perpendicular to the segment. Let's cross out is a line that. Because it doesn't have to be a line, it could also be a ray or a segment. So let's just say a perpendicular bisector bisects the segment and is perpendicular to the segment. That's fine. You could put A instead of the, but it doesn't really matter. We understand what it means. So if I have a segment, I'm going to draw this one between, I don't know, between the 2 and the 4. So that means the middle would be at the 3. So if I have this segment, let's call it A, B. I can draw a line or a ray or a segment or anything I want that cuts it in half, right? So in our case, let's just make it a line. And it's going to be perpendicular to the segment. That's one of the requirements. And it cuts it in half. So this piece is going to be equal to this piece. Okay? So let's say this is line L. So line L is the perpendicular bisector of segment AB. Okay, that's good enough. Now, let's see why we wanted to know that. Okay, because the next word we're going to talk about is called the circumcenter. The circumcenter. Alright, the perpendicular bisectors of the sides of a triangle are concurrent. That's the first thing. How do I want to state this? The point of concurrency comma called the circumcenter comma may or may not be inside the triangle. Now let's skip a line and say let me see here. Oh. The circumcenter is the center of a circumscribed circle about the triangle. Okay, let's put our little arrow down here because we're going to have to try to make this. Okay, so let me think about this for a second. How can we do this the best way? I think I have a good idea. Here's what I want you to do. Go to the top. Now let me just think about this for a second. So this card is 6 inches long. So I think we should make 2, 2.5. No, it's got to be, if it's a 1.5, let's make it a 1 inch, so a 1 inch radius. So here's what we're going to do. We want to go halfway down, so measure down. This is a 6x4 card, so measure down 2 inches and just put a dot, just so we know where it is. And on the other side also measure down 2 inches and just put a dot. Now line your ruler up on that from the 0 to the 6. Okay? Now make a dot at, let me think about this. If we're going to go 1/2 inch to 2.5 inches. Okay. So at 1.5, put a dot, and also at 1/2, put a dot, and then at 5.5, put a dot, and at 4.5, put a dot. Okay. Now here's why we did that. Take your compass and put your compass so that it's on the second dot, and line up your hole so that it's on that first dot. And make a circle. Okay. Do the same thing from the other side. Now let's line our circle, our center up on this dot, and this one should already be lined up because we made it the same length. So we have 2 circles. Alright, I wanted to make the circles first so that way we know how to draw our triangles. So in this first circle, we're going to draw the base of a triangle. And this one is going to be an acute triangle. Okay. Now, we got to draw the perpendicular bisectors of all those sides. So let's start with this side. This side is about 4.7 centimeters. So that means I got to make it 2.35, which is right about here. Okay. So I'm going to make a perpendicular bisector that goes right through that point. Just like that. And we know that this segment is congruent to this segment, and this line is perpendicular to this side. Perpendicularly bisected that bottom line. Now let's turn the triangle this way, and let's perpendicularly bisect this side. So this length here is also about 4.7 So I'm going to go again to 2.35. Okay, and I'm going to make this as best as perpendicular as I possibly can by eyeballing it. Okay, and this line is perpendicular. And it cut these two sides, so now this piece and this piece are the same, this whole piece here. Okay, now let's cut this side in half, our last side. This is about, let's see, pretty much 3.3. So 1.65. Right about here. Now we don't have to be perfect, we just got to be close. Right? And I'm going to perpendicularly bisect that side. And we know that this piece is the same length as this piece. So, there you have it. This point in the middle is the center of this triangle. Now remember when we did the in-center, you see how the circle is on the inside of the triangle? Right? That's called an inscribed circle. That's why that's called the in-center. In this one, the triangle is the one in the middle, and the circle is doing what's called circumscribing the triangle. So it's around the outside of the triangle, touching it at all of its vertices. So that's why we call this inside point here this is called a circumcenter. Okay? Now let's see what happens when we have an obtuse triangle. Okay? So let's make an obtuse triangle. Okay. Now, we have to do the same thing that we did before. This side is about 3.5, so I'm going to go to 1.75. Make a little mark. Okay. Okay, so this is perpendicular. And this side is equal to this side. Congruent. Now I'm going to go to this side. This is 2.4, so I'm going to go to 1.2. Alright, and we know that this side is congruent to this side. And now we got one more side. Oh, I didn't draw my perpendicular marker. And we got one more to do here. This is 4.8. So I'm going to go to 2.4. And as you can see, exactly what's happening is exactly what I want to happen. Now, they're all meeting at a point outside of the triangle this time. Do you see that? So if it's an acute triangle, the circumcenter will be inside. But if it's an obtuse triangle, the circumcenter is outside. But it's still the center of the circumscribing circle. So this is the circumcenter. Okay? So those are our two pictures for this. Now, let's see. That is actually all the definitions that we'll need for the next problem set. Okay? Alright, this is G.G.21. This will be numbers 202 through 210. So let's see, in which triangle do the three altitudes intersect outside the triangle? Well, if we go back in our note cards, this to the altitudes, right? Now, we had two examples. This is the orthocenter. This is where the altitudes intersect. It's called the orthocenter. When you have an acute triangle, it's inside the triangle, right? But when you have an obtuse triangle, the orthocenter is outside of the triangle. So it's when it's an obtuse triangle. So this one is just choice 3. In a given triangle, the point of intersection of the three medians is the same as the point of intersection of three altitudes. Which classification of the triangle is correct? Let's see here. So the three medians, that was centroid, right? If those three medians met at the same place as it says the three altitudes, that was the orthocenter. So we have these two cards are what we're looking at. That would have to be, the only time that that would happen is if it's an equilateral triangle. Okay? Let me just see something. An equilateral triangle. Let's think. Let's try it out real quick. Because I'm not 100% sure, to be honest. I mean, I think it's equilateral. That just seems to make sense, but I have to prove it to myself. So I made that side 2 inches. Now I gotta go up 60 degrees because all the angles in a equilateral triangle Okay, I just marked 60 degrees. So now I'm going to go 2 inches towards that 60 degree mark. Okay, and then this should be 2 inches now left over. And you can see that it is. Between the 1 and the 3, that's 2 inches. So here's an equilateral triangle. All the sides are 2 inches, all the angles are 60 degrees. Now, the median is going to be, it's going to go from the vertex right to the middle of each side. Yeah, I mean, now that I'm thinking about it, it definitely is going to be the equilateral triangle, but let's just see and make sure. Let's draw the 3 medians first. Remember, the median goes from the vertex to the middle of the opposite side. Okay? So, in this triangle, we actually know that all of these pieces will be the same. Okay, because it's equilateral. And they're all cut in half. So if they were all 2 inches and they were all cut in half, now they're all 1 inch. So the medians meet right here. That's the centroid. And these are also going to be the altitudes. Okay, so actually you can see right away that it is, in fact, an equilateral triangle. Now, let's, for this one, for number 202, I just want to come back to that for a second. We really need to put on this page the picture, the orthocenter picture. So what we need to do is, okay, we need to draw an obtuse triangle any obtuse triangle will do. Now, it says the altitudes. So what we have to do, first I'm going to draw the altitude from this corner so it goes straight down. So what we have to do is extend this side with dashed lines. Right? And now we have to come straight down. And we need to extend that altitude with the dashed line down also. Okay. So all I did is I extended it down. Alright. Now let's draw the altitude of this side. This is the easiest side, right? Because it just comes straight. Come straight down, and we're going to extend this one now too, and you see why I made that line extra long now, because these two actually have to cross up there. Alright, so let me actually extend this one a little further. Okay. So you could see, so far we have this. Now we have to drop an altitude down from this side. So let's extend. We have to drop it down from this vertex. So let's extend this side just enough to be able to draw an altitude straight down. Put a right angle mark, and now we also want to extend that side. See, now really we're going to fudge it a little bit because they're supposed to cross. Okay, so I'm just turning my ruler enough so that it'll meet right at the same point down there. Because remember, since we're drawing this, it's never going to come out exactly right. It's going to be close, hopefully. Alright, but you see how I just had to move the ruler a little bit? Sometimes you have to do that. It's not a big deal. So now, notice how for our answer was obtuse triangle. When you draw the altitudes of an obtuse triangle, they meet outside of the triangle. Okay? And again, that is called the orthocenter. Alright? Now, this second one, there's two labels for that point. When the medians met, it's called a centroid. And when the altitudes meet, it's called an orthocenter. Okay? Now, let's move on. For a triangle, which 2 points of concurrence could be located outside the triangle? Alright? Now, we just talked about one of them, right? The orthocenter can be outside of the triangle. And there's another one that we talked about, and it's called the circumcenter. Remember this one? See, for an acute triangle, the circumcenter's in the triangle. But for an obtuse triangle, the circumcenter is outside of the triangle. And the circumcenter is where the perpendicular bisectors of all three sides of the triangle meet. That's what circumcenter is. Right? We talked about that on the other side of the card. So we have circumcenter and we have orthocenter. Okay? So let's write those answers down. Okay. And let me think for a second. We should draw a picture of these, okay? Even though this seems tedious, you really need to practice this. So, this time I'm going to draw my my obtuse triangle a little smaller, so hopefully we don't take up the whole page again. So I'll go 1.5 inches, and I'll make it a little less obtuse. I'll go 1 inch. Now this should make it a little bit so for the orthocenter, that's the one that we just did, right? We have to do the altitudes of all three sides. So here's the first one. And we need to extend that a certain amount. Not exactly sure how much yet, but hopefully that will be enough. Maybe not, we'll see. Now let's do this side. Yeah, it looks like that'll be more than enough. Okay, and now we have one more side to do. Let's see. Why am I not seeing this clearly? This side. Sometimes even I get thrown off here. So first we're extending this side so that we can draw our altitude down to this side. And what we'll see when we extend that altitude, sure enough, they all crossed outside, which is called the this is called the orthocenter, when it's the concurrency point of the altitudes of the three sides of a triangle. Now we had another choice here, the circumcenter, right? So if we have, let's draw one more obtuse triangle. Now you can see it always deals with obtuse triangles when it meets outside the whenever it meets outside of the triangle, it's always because it's an obtuse triangle. And that's always the case for the orthocenter and the circumcenter. Now the circumcenter is where the perpendicular bisectors meet. So this is about 4 centimeters, so this one's going to cross at 2. So there's one. Now this one is about 2.5, so we want to go to 1.25. Okay, so I'm going to have to extend that first line I drew a little bit. Right? And And so this is perpendicular. Now these are perpendicular bisectors. These are not altitudes. And then this side is 5.6, so I got to go to 2.8. I got to draw the perpendicular line. And I'm just going to make sure I go right through that third point there, so I might have to fudge it just a little bit. Okay. So, as you can see, the three perpendicular bisectors of an obtuse triangle meet outside, and that is called the circumcenter. So it's orthocenter and circumcenter. Next one. In the diagram below of triangle ABC, AE is congruent to BE. So I'm putting one mark on each line. AF is congruent to CF. So I'm going to put 2 on each line. And CD is congruent to BD. So that means that each one of these is a median, right? Because it goes from the vertex and it bisects the opposite side. It goes from the vertex and it bisects the opposite side. And it goes from the vertex and it bisects the opposite side. So these three lines are medians. And where the medians meet is called, if we look back at our definitions that we went over, alright, we talked about medians, and then right after that, right, see how the median bisects the opposite side? Where the medians meet is called the centroid. See? They meet right at what's called the centroid. So, the answer to this problem is the centroid. Did we circle the answer to the... Yes, we did. Okay. Let's go to the next one. The diagram below shows the construction of the center of the circle circumscribed about triangle ABC. So remember, we can go... Remember what these pictures? Right? When a circle circumscribes a triangle, okay, we're going to be talking about the circumcenter. Well, let's see what the problem asks us. This construction represents how to find the intersection of, well, the circumcenter deals with the intersection of the perpendicular bisectors, right? All of the perpendicular bisectors meet at what's called the circumcenter. So, the answer is the perpendicular bisectors. Okay? In the diagram below of triangle ABC, segment CD is the bisector of angle BCA. So that means that this angle and this angle are congruent. Okay? BCA is bisected by segment CD. AE is the bisector of angle CAB. So this angle is congruent to this angle. AE cuts this angle BAC or CAB into two congruent parts. And then AE, we just did that. So, and BG is drawn. So here's BG, and they don't tell us anything about it. But you do see that it meets right at that middle point where the other two angle bisectors cross. So which statement must be true? Well, this must be an angle bisector if it meets at this point here where these other angle bisectors meet. And that means that this angle must be congruent to that angle, which is choice DBG congruent to EBG. And that point Let's go to the card that we did. Okay. We talked about angle bisectors, right? And where the angle bisectors meet, the angle bisectors of a triangle are concurrent. The point of concurrency called the incenter. All right, let's take a look at the picture. See where all the angle bisectors meet? They meet at what's called the incenter. Okay? So that's it for 207. Oh wait, let's label this incenter. Which geometric principle is used in the construction shown below? Okay. Well, if you remember how to do constructions, right, what they're doing is they're bisecting these angles. You see how they're bisecting the angles? This is how you do a construction of bisecting angles. And when you do that, you get what we just talked about. You get the card I just had out. You get the incenter, right? The angle bisectors of a triangle are concurrent. The point of concurrency is called the incenter. And that's what it looks like. See that? All those angles are cut in half. And you can, and the circle is inscribed in the triangle. That means it's inside the triangle. So, and it's called the incenter. So the intersection of the angle bisectors of a triangle is the center of the inscribed circle. That's it. Okay? Be careful, because the next one was circumscribed. But that, remember, that means when the circle's on the outside of the triangle. Inscribed, inside, in center. That's why they named it that. Then if it was circumscribed, right, it would be circumcenter. Okay. Let's look at the next one. The vertices of the triangle in the diagram below are given and they're plotted. Okay. So what are the coordinates of the centroid of triangle ABC? Remember, the centroid goes from the vertex to the middle of the opposite side. So if this side is 1, 2, 3, 4, 5, 6, 7, 8, then we go 4 over, 1, 2, 3, 4, and we make a line down there. And then we look at it this way, and this side is up. Well, this is how we can look at this. To get from this point to this point, we go up 4 and to the right 1, 2, 3, 4, 5, 6. So if I want to go halfway, instead of going up 4 and to the right 6, I'll go up 2 and to the right 3. So there's the middle of this side. And so it goes from the vertex through the middle of the opposite side. Okay, and you can already see where it is, but we're just going to double check with our last side. So to get from B to A, I have to go up 1, 2, 3, 4, 5, 6, and to the right 1, 2, 3, 4. So instead I'm going to go up 1, 2, 3, which is half of 6, and to the right 2, which is half of 4. And I'm going to go from this vertex through that side. And now you can see the coordinates for the centroid, okay, which is at 7, 5. Okay, and just so you know, you needed to know that the medians meet at what's called a centroid, right? We talked about medians. And then we talked about the centroid is where all the medians meet. Okay? And we haven't gotten to one of these yet, but we will get to these where the centroid divides the medians into a 2-to-1 ratio. But also, there's your picture. Okay? The centroid is where the medians meet. And we got one more in this section. Triangle ABC has vertices 3, 3, 7, 9, and 11, 3. 3. And that is A, B, C. Let's just draw our triangle in. Okay. Determine the point of intersection of the medians and state its coordinates. So they like to give this problem because these are regions problems, right? Okay, so this side is 8. So we go 4 and we draw that line from the vertex through the middle of the opposite side. That's why it's called a median. And then to get from B to C, we go to the right 4 and down 6. So instead we'll go to the right 2 and down 3, which is halfway. And we can draw that part of the line. Now you can already see what it is, but we're going to just do the other one too because you got to show all your work. So to go from A to B, we go up 1, 2, 3, 4, 5, 6. We go to the right 4, so instead we'll go up 3 and to the right 2, which is half of 6 and 4. And like that. Okay? So this point is called the centroid, and the coordinates are 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 7, 5. That turned out being almost the same problem. That was the exact same problem as the last one. So they asked the same problem on the regions, but this time they didn't graph it for you. Okay? But again, make sure you review those cards on median, right? And on the centroid, which is where all the medians meet. Okay? So that's why we do these cards, because you need to know the concepts, not just how to do the problem. Okay. So that's the last problem of G.G.21. Now we're going to move on to, there's a couple of problems in what is G.G.43, and they have to do with centroids. So we're going to do those right now. And it's only 211 through 216, so it's a couple more problems. Okay. So these problems deal with standard G.G.43, and they're 211 through 216. So let's look at the first one. In the diagram of triangle ABC below, Jose found centroid P by constructing the 3 medians. Okay, so he found this centroid right here by constructing the 3 medians. So this side is equal to this side is equal to this side, and this side is equal to this side, because the medians cut the opposite sides in half. Okay? He measured segment CF and found it to be 6 inches. Okay? So CF is 6 inches. If PF equals X, so this little piece equals F, they want to know which equation can be used to find X. So now let's look at our card about centroids, because it says what we need to know here. Here's the important part down here. The centroid divides the medians into a 2-to-1 ratio. The section of the median nearest the vertex is twice as long as the section near the midpoint of the triangle's side. Let's see what that looks like in a picture. Here's the centroid. You see how the little piece is half as big as the big piece? Same thing over here, right? The little piece is half as big as the big piece. And the same thing over here. the little piece is half as big as the big piece. That's that 2-to-1 ratio they're talking about. So when you have a centroid, it cuts it into a 2-to-1 ratio. This is 2-to-1, this is 2-to-1, this is 2-to-1. That means that the bigger side is twice as big as the little side, or the little side is half as big as the big side. So let's apply this to this problem. Okay, we know that if PF is x, then CP would have to be 2x, right? And we know that the whole thing is 6, so we know that x plus 2x equals 6. And there it is. Okay? Okay, in the diagram below, we have a bunch of medians, and they intersect at the centroid, G. So I just always like to draw in my, showing that I know that my sides are the same length here, that they're bisected. So if CF is 24, what is the length of FG? Well, let's call it FGX. And we know that GC would be 2x, right? It's got to be twice as long because this is the longer side. So it's double the smaller side. And we know the whole thing is 24. So we know x plus 2x equals 24. 3x equals 24. X equals 8. And FG equals x, which is 8. Okay? Again, that has to do with this bottom line. They're all going to have to do with this bottom line and this picture. Okay? 213, same deal. This is as big as this is as big as this, and this is as big as this because they're medians. They intersect it here at G, and the length of FG is 12. FG is the smaller one, so we know that GC is 24, right? Because it's twice as big. So what is the length in centimeters of GC? We just figured it out. GC equals 2 times 12, which equals 24. Again, it has to do with the bottom line. The ratio is 2-to-1, and the picture. (214) in the diagram below, point P is the centroid. The centroid is where the medians meet. So I know this is congruent to this is congruent to this, and this is congruent to this. And I know these are in the ratio 2-to-1, 2-to-1, 2-to-1. So PM is 2x plus 5. BP is 7x plus 4. What is the length of PM? Okay. Well, we know that BP equals 2 times PM. Right? It's twice as long as PM. BP is 7x plus 4 equals 2 times PM is 2x plus 5. So 7x plus 4 equals, distribute, that's 4x. Distribute, that's plus 10. Subtract 4 from both sides. I get 7x equals 4x plus 6. Subtract 4x. I get 3x equals 6. Divide by 3. I get x equals 2. It says, what is the length of PM? Well, PM equals 2x plus 5. So PM equals 2 times 2 plus 5. PM equals 4 plus 5. PM equals 9. So Don't leave your answer as 2, which is of course one of the options, right? You have to plug it back in for what they're asking you for. They're asking you for PM, which is 2x plus 5. Again, this had to do with the centroid fact, that it divides it into a ratio of 2 to 1, just like this picture. Almost there. 2 left. ABC below. P is the centroid. And BF equals 18. I know this side equals this side equals this side, and this side equals this side. Okay, what is the length of BP? Well, BP is 2x, and PF is x. And we know that BF, the whole thing, equals BP plus PF. So 18 equals 2x plus x. 18 equals 3x. Divide by 3. X equals 6. Now it wants BP. BP is 2x. BP is 2 times 6. BP is 12. Last one on this topic. Triangle TEM. We have medians TB, EC, and MA, and they intersect at the centroid D. Okay, the medians cut the sides into congruent halves, and they cut the medians into ratios of 2 to 1, 2 to 1, 2 to 1. So TB is 9. TB is 9. Now we know this is 2x and this is x, right? They want to know what TD is. Well, we know that TB equals TD plus DB. Now TB, they told us, is 9. TD is 2x plus DB is x. So 9 equals 3x. Divide by 3. X equals 3. They want to know TD, which equals 2x. So TD equals 2 times 3. So TD equals 6. This one was not multiple choice, so there you go. Okay, so those all had to do with the centroid, alright, that it divides the medians into a 2 to 1 ratio, similar to this problem. Okay, each one of these is, the big one is twice the little one. So you could say x and 2x, x and 2x, x and 2x. Alright, now that is the end of this lesson.